The last topic for the course is section 8.7, Indeterminate Forms and L'Hopital's rule. Now recall that earlier in the semester that there were limits that we would run these limits and we would end up with the indeterminate form. And the indeterminate form, when you attain that through direct substitution, you realize that the limit is not actually equal to these indeterminate forms. Here they are, 0 over 0, infinity over infinity. And even these forms over here are considered to be indeterminate. The reason is, normally when you divide by 0, the answer is undefined. The reason it's undefined is because the answer is infinite. But with 0 on top of the fraction, typically 0 on top of a fraction means that the fraction is worth 0. But same over same could be worth 1, actually. Well, it's actually none of the above. So 0 over 0, infinity over infinity, these are confusing forms that are just undefined. In fact, they're especially undefined. We call them indeterminate. Now remember, when we did obtain the indeterminate form through limits, and this is for limits, what we did was we would try to evaluate the limit using direct substitution. So this is a limit as x approaches 2. And we would plug x equals 2 in here, we would plug x equals 2 in here, and then we would say, is it really equal to this fraction? Well, notice by direct substitution, I got 0 over 0. And of course, the first thing you do when you run into that with a limit is cross it right off. It is not correct. It is not the answer for the limit. In fact, if you look a little more closely, you realize that there really is an answer. It's just that the function itself is undefined at x equals 2. Now a limit, going all the way back to the beginning of the semester, a limit is not the value of the function. It's actually to what y value were you headed. And you can see that if you head from the left or you head from the right, all roads lead to y equals L. It's just that we don't know what L is at this moment. Now, the resolution for obtaining this indeterminate form, in fact, the indeterminate form often was an indicator that there really is an answer to the limit. It's just that we don't know what it is yet. And in this particular case, what we would use would be the dividing out technique. So, for this one, we would factor x squared minus 4 into its two corresponding factors, and then we would divide out the corresponding factor. Actually, we call that the offending factor. It's the very factor that's causing the limit to be 0 over 0. Once it's divided out, you can then plug x equals 2 into your limit with direct substitution, and we get the answer, which is 4. Now, dividing out technique was a method we used to reveal the hidden answer. So actually, if we go back to our graph over here, we would see that now we know that L is actually equal to 4, whereas before we had no idea what y value we were headed towards, and now we do. It's 4. So, this revealed the hidden answer, 4. Now, L'Hopital was a French mathematician, and what he discovered was there is an alternative method to finding the answer for a limit which is undefined because it's indeterminate. And the alternative is actually very creative and very interesting, and that is that if you run a limit as x approaches c on a fraction, and you obtain the indeterminate form, L'Hopital discovered that that limit that you're trying to obtain, again, it has to come out to be the indeterminate form, because if it is not the indeterminate form, then you already have your answer. But if it is the indeterminate form, the suggestion is try a new limit. And here's the new limit right here. Hard to prove, but it does work, and it is true, and that is that we would run the limit as x approaches c of, instead of f over g, the original functions, we run the limit on f prime over g prime. Now, I do want to make note that this is not the quotient rule, because it's f prime over g prime. It's actually what we thought the derivative of a quotient would be, and it turned out not to be the case. So this is not the quotient rule. In fact, this isn't even the derivative of f over g, because in order to do that, you would actually run the quotient rule. This is for limits only. It's for limits only and for limits of fractions, and only limits of fractions that resolve to be the indeterminate form. So I've got a three-step checklist for you, and L'Hopital's rule is applicable only when it's a limit, only when you're taking the limit of a fraction, and only when the answer turns out to be the indeterminate form. So another three-step checklist. Now if you pass all three, then you're allowed to use L'Hopital's rule. And again, L'Hopital states that if the limit's not working out for you, if you're getting the indeterminate form, his suggestion is, try this instead. Try the derivative of f on top, derivative of g on the bottom, and rerun the limit. And perhaps you will get a result that is not indeterminate. So let's take a look at how we would do this on this particular problem. All right, so we know that if we try direct substitution on this problem, we get the indeterminate form. We've tried that already. We then used the dividing out technique, successfully got our 4. But let's go through our three-step checklist. It is a limit, of course. That's a check. It is a limit of a fraction. That's also a check. And number 3, it is definitely a limit that leads to the indeterminate form. No question, because we tried it with direct substitution. So L'Hopital's rule does apply. Now L'Hopital suggests trying a new limit. That would be as x approaches 2, and on the top we put f prime. F prime would be 2x. And on the bottom we would put g prime. And g prime is simply 1. L'Hopital says try again, this time with direct substitution. In goes the 2. 2 times 2 is 4 over 1. And notice that we do indeed get the right answer. So, L'Hopital's rule is another powerful method for obtaining a limit when you are running into the indeterminate form. The indeterminate form is frustrating because it's telling you that the function is undefined there in this special way. It's usually a little hole, which also tells you that the limit does exist. It's just that we don't know what it is. So one method is dividing out, and now we have a new method. You'll notice we had to save this for the end of the course because when we first did limits, we didn't know calculus, so we couldn't have done f prime over g prime. Now, this is very useful for limits. And it's particularly useful when either the dividing out technique or, we had another technique, by the way, it was called rationalizing the numerator. And it's very useful, in particular, when those simply cannot be used. Well, here's an example. We have a limit as x approaches 0 of e to the 2x minus 1 over x. Now, I will say this. It is actually factorable. E to the 2x minus 1 is the difference of two squares. So it actually is factorable. And it would look something like this. E to the x plus 1, e to the x minus 1. So it is factorable, but that's not going to help us because these are not the offending factors. It is the difference of two squares, can be factored, but neither one of these are the offending factors because when you plug 0 into them, you actually get, for the first one here, you would get 2. And the second one, you get, well, second one you do get 0, I suppose, but there is no factor corresponding to these in the denominator to cancel out. So I don't think that that's going to be a valid approach. So I'm not going to do that, even though you can factor. I can't really find an offending factor to cancel. So the dividing out technique's not going to work. There's nothing to divide out. Something to factor, but nothing to divide out. So the first step, anyway, would be to try direct substitution. So in goes the 0 here and here. I get e to the 0 minus 1, which is 1 minus 1, which is 0 over 0. So we tried direct substitution, and it pretty much failed because we got the indeterminate form. This is more of an indicator that there is an answer. It's just that we don't know what it is. So let's try to see, number 1, does L'Hopital's rule apply? And number 2, if it does, let's apply it. So there's that three-step checklist. Number 1, it's a limit. Yes, it is a limit. Check. Number 2, we're taking the limit of a fraction, also check. And number 3, we are getting the indeterminate form. So, absolutely, L'Hopital's applies and we can use it. It's really important to know when L'Hopital's applies and when it does not, because there's a temptation to use it sometimes when it's not called for, and the answer you get will actually not be the correct answer. So make sure that it truly applies before you apply it. Okay, now, here's the original limit. This is the one that we would like the answer for. I'll highlight that so we can take a look. I know that direct substitution fails, so therefore we apply L'Hopital's rule. L'Hopital's rule says, try again. Try the limit where you take the derivative of the top and the derivative of the bottom. Great. That's what we're going to do. Okay, let's take a very careful derivative of our numerator. The derivative of e to the 2x. Well, you know the derivative of your exponential. The derivative of e to the 2x simply is e to the 2x. But don't forget your chain rule, guys. Here it is. The chain rule, you gotta do it. Derivative of 2x is 2. Now the derivative of x on the bottom is certainly 1. And so I've got 2e to the 2x over 1. Okay, now let's try direct substitution. In goes my 0. So I get e to the 2 0, which is e to the 0, and we know what that's worth. Anything to the 0 power is worth 1. So my answer is 2. There's my limit. So L'Hopital's rule definitely applies. We took the derivative of the numerator and denominator separately, and then we plugged x equals 0 into it one more time, and we got a result. The answer is 2. Now, if you were to graph this curve here, and I encourage you to do so on your graphing calculator, you will notice that around x equals 0, we should be in the vicinity of y value 2. Now, your calculator has a little bit of a technological limitation in that it actually does not draw the open circle over the coordinate 0, 2, as we would if we were to graph this. So it just basically doesn't plot a point there. So what's happening is that the pixel that is used for the y-axis, may seem like part of the graph, but it's really not. But it should be in the vicinity of 2, and that's a good way to verify that this is working. Okay, let's take a look at another example. So right here I have the limit as x approaches infinity of the natural log of x over x. The first attempt should always be direct substitution. So in goes infinity into here, and we get the natural log of infinity on top and infinity on the bottom. Now, I drew a little graph of the natural log curve here so that you can see that as x approaches infinity, the arrow is indicating that y also goes to infinity. The natural log of infinity is heading towards infinity. And so then we get infinity over infinity. Of course, we cross that off and say, nope, that is not the answer for a limit. The indeterminate form never is. So we refer to our three-step checklist. Number 1, is this a limit? Yes. Number 2, is this the limit of a fraction? Yes. Number 3, are we getting the indeterminate form? Yep. Now, don't forget to run this three-step checklist because, again, as I mentioned, there are situations where you'll be tempted to use L'Hopital's rule, and actually, you shouldn't use it. And when you do use L'Hopital's rule where you shouldn't, you'll actually get the wrong answer. So be careful. Make sure you run this three-step checklist first. Now, it's time to run L'Hopital's rule. In fact, we're going to rerun this limit by taking the derivative of natural log of x is 1 over x on top. The derivative of x is 1 on the bottom. So the new limit is basically the limit of 1 over x as x goes to infinity. So in x goes, or infinity goes into x, actually, right there, and you get 1 over infinity, which actually is a finite value. It's 0. So we get our answer, which is x equals 0. Finite over infinity is worth 0. Infinity over infinity would be indeterminate again, and we'd still not have the answer to this problem. So again, there's another thing that you could do. You could take your graphing calculator, you could graph this original function, and you should notice that around x equals infinity, you're not going to really see that. So you would have to scroll your graph very far to the right and take a look at, well, where is this graph headed? It should be headed to y value 0. In other words, this means that, at least on the right side, as x approaches infinity, y is approaching 0, and that would be a horizontal asymptote. So our x-axis should look like a horizontal asymptote, at least on the right side. If you want to know about the left side, you would have to send x to negative infinity and try this whole process again. But I'm assuming that on this curve, it should also be a horizontal asymptote. Okay, so let's take a look now at another example. This one. So we're going to take the limit as x approaches 0 of this fraction, e to the 2x plus 1 over x. First thing you should try is direct substitution. So in goes that 0 here and here. Now 0 goes in, so we get 2x plus 1 up there. We get e to the 1 actually, e to the 1, which is just e. On the bottom we do get 0. Now that's not indeterminate. It certainly is undefined though. Finite over 0 is infinity. And you can stop right there. That is the answer to this problem. The limit is infinite. And you know what happens when the limit's infinite? We say that the limit does not exist. So let's go through the three-step checklist. Should we use L'Hopital's rule on this problem? Number 1, it's a limit. Number 2, it's a fraction. Number 3, do we get the indeterminate form? And the answer is no, we do not get the indeterminate form. Therefore, we should not use L'Hopital's. And it is tempting, isn't it? We're getting this undefined result. And if you run L'Hopital's rule, what you would get would be, well, let's see. I think you would get 2, actually. Or, wait a second, would you get 0? So e. You would get 2e, I believe, if you plugged x equals 0 into the new L'Hopital's version. 2e. That is not the answer. The answer is infinity. The limit does not exist. So don't use L'Hopital's rule because we already have an answer. We already have an answer. If you already have an answer, that's your answer. Let's not try to get another answer. So the only time you dig deeper is when you have the indeterminate form. And the indeterminate form is 0 over 0, infinity over infinity. 1 to the infinity power, 0 times infinity, and 0 to the 0 power. Those are all indeterminate. Oh, one more. Infinity minus infinity is also indeterminate. 0 or infinity itself is a legitimate answer, and you can simply go with that. That is your answer. Okay. What about running L'Hopital's rule more than once? Would that work, and is there an opportunity to do so? Well, again, you should only be running L'Hopital's rule if you can pass the three-step checklist that we have now for L'Hopital's rule. Now, the first thing you should do is, well, before you do anything, try direct substitution. It might just work, and then you won't even need L'Hopital's rule. So in goes minus infinity. Minus infinity goes up here too, and we get minus infinity squared over e to the positive infinity because it's a negative x and a negative infinity, so it's e to the positive infinity. Now minus squared is positive, but infinity squared is just infinity. You can't get any higher than infinity. And e to the infinity, well, if you take a look at the e to the x curve, you can see that as x goes towards infinity, so too does y up here. So it's infinity over infinity. Therefore, indeterminate. Okay, three-step checklist. Number 1, we are running limits now. Number 2, this is a fraction. At least, I mean, over here, the original function is a fraction or a rational function. And, yep, number 3, we are getting the indeterminate form. So, yeah, L'Hopital's rule is definitely called for. Let's try it. So, over here, since L'Hopital's rule is called for, we are allowed to do this. In fact, we rerun the limit, but we take the derivative of the top, and we take the derivative of the bottom. And if you're curious as to where this minus came from, that came from the chain rule. That is a fundamental rule that we must remember in pretty much everything we do when we take derivatives. Even use substitution, because you're going to have to do a du dx. So almost every problem, you really need to look at that chain rule carefully. What I did was I took the derivative of e to the something, which just is e to the something, and then I took derivative of minus x. And I put it right here. Derivative of minus x is minus 1. Okay, let's try again, guys. Now that we have a new limit to work on. I want you to plug x equals infinity in here and also in here into our x. So I'm doing it over here actually. So let's plug it in here and over here. Better place. So go ahead and plug in minus infinity, and what do we get? Well, on the top you get minus 2 infinity. On the bottom you get minus e to the infinity, which is minus infinity. The minuses cancel, and well, 2 infinity is really infinity. You can't get any bigger than infinity. So look what we got. Indeterminate form again. Now realize that the answer to this limit here is the answer to the original limit, which is actually right above it here. So if we could find the answer to this limit, we would have the answer to the original. Well, we're trying to find a limit. It's the limit of a fraction. And the answer is the indeterminate form, so therefore L'Hopital's rule definitely applies. Now if L'Hopital's rule definitely applies, then we can do it again, and we should do it again. So therefore, we should do this one more time. So L'Hopital's rule does apply, and L'Hopital's rule says try your limit again by taking the derivative of the top and the derivative of the bottom, and don't forget your chain rule. So 2x derivative is 2. And minus e to the x, well, what is that? Well, the e to the minus x derivative just is e to the minus x. We get that. But don't forget your chain rule. The derivative of that little minus x is a minus 1. And that minus 1 comes out and hits the minus already in front and becomes positive. Okay, one more time. We're going to take our x and send it off to minus infinity. In it goes right there. So e to the minus infinity. Well, e to the minus infinity is just e to the infinity, and e to the infinity is infinity. And 2 over infinity, well, finite over infinite, that's 0. That is not indeterminate, and that's not even undefined. So therefore we have an answer to this final limit, which gives us an answer to this limit, which then tells us the answer to the original limit, which is right over here. So that's how we run L'Hopital's rule more than once. We run it each time that we are stuck with the indeterminate form. But of course, remember, there's 3 steps. Fraction, limit, indeterminate form. Okay. What about a limit that yields the indeterminate form, but it's not a fraction? Well, here's an example. This example, I'm taking the limit of x to the minus 1 times e to the x over 2. And of course, the very first thing you should try is direct substitution. So I went ahead and put x equals infinity in there, and I put x equals infinity up there, and this is what I got. Infinity to the minus 1, e to the infinity over 2. Now, infinity over 2 is just infinity. You can cut infinity in half, you'll still be there. And infinity to the minus 1, there's an upside down infinity, and that's 1 over infinity. Now, 1 over infinity is a valid result. That's 0. But e to the infinity is infinity. I mean, you can look at the e to the x curve to realize that, because off it goes off the page. Well, 0 times infinity is also an indeterminate form because it's confusing. 0 times anything should be 0, but anything times infinity should be infinity. So which one is it? Well, it's none of the above. It's definitely undefined, but it's a special kind of undefined. It's indeterminate. So let's go through our checklist. Maybe L'Hopital's can bail us out on this one. Number 1, it's definitely a limit. Number 2, it's the limit of... No, that's the problem. It's not the limit of a fraction. Now, we are getting the indeterminate form. That's true, but it didn't pass step 2. Therefore, right now, we're not allowed to run L'Hopital's. In fact, how would you run L'Hopital's where you're supposed to take the derivative of the top and the derivative of the bottom? There really is no bottom other than 1 being a denominator, I suppose. So I would rewrite this first as a fraction. That would be your first step. Rewrite as a fraction. Now, this is not very difficult to rewrite as a fraction. In fact, what's going to happen here is you're going to take this x to the minus 1 and rewrite it for what it is, it's really an x in the denominator. So now you have e to the x over 2 on top, you have an x on the bottom, and who knows, maybe it will work in this form. So I said, let's just try it as a fraction by plugging x into both the numerator and denominator, and look what I found. Another indeterminate form right here. So at this very moment, this problem is definitely a limit. It's definitely the limit of a fraction. It's definitely an indeterminate form. It's even slightly different than this one, but it's still indeterminate. L'Hopital says, yes, you can use L'Hopital's rule, hopefully, to get a result on this one. So now, let's use L'Hopital's rule. L'Hopital's rule says, take the derivative of the numerator, take the derivative of the denominator, and try your limit again. Now, we love the derivative of e to the x over 2 because it is just e to the x over 2. That's how easy exponentials are. But what about our little 1/2 here? The 1/2 is there because it's the often overlooked chain rule. The derivative of e to the x over 2 certainly is just e to the x over 2, but what's the derivative of x over 2? It's just a half, and it should be chained next to it, either to the left or to the right. You notice I put it on the left. L'Hopital suggests, try again. Try plugging in infinity into the problem. It would go in here, and it would also, oh, that's the only place it goes, actually. So that's the only place I have for it. So I plugged infinity in. See, I put it in right there. And I got e to the infinity right here. But e to the infinity is infinity, and a half infinity is infinity. So that's a conclusion. The answer to this limit is that the limit is infinite, and therefore the limit does not exist. That's what we normally write. So that is not an indeterminate form. Remember, 0 or infinity is a valid answer for this problem. And when infinite limits occur, we say that the limit does not exist. Okay. So in summary, when you're running a limit, and it's the limit of a fraction, you can use L'Hopital's rule, and L'Hopital suggests that you try this new limit. Don't forget to check to make sure that you're allowed to use L'Hopital's rule. 3-step checklist. Number 1, it's a limit. If it's not a limit, then L'Hopital's doesn't apply. So if it's just f of x over g of x and you evaluate it, boy, if you get the indeterminate form, you're done actually. You just say that the function's undefined. There has to be a limit in order for us to dig deeper anyway. Number 2, has to be the limit of a fraction. If it's not the limit of a fraction, sometimes you can make it the limit of a fraction by moving something to the denominator. And finally, number 3, you should be getting the indeterminate form before trying to use L'Hopital's rule. So when you get the indeterminate form, like 0 over 0, infinity over infinity, what else? 0 to the 0 power. Here's an odd one. 1 to the infinity is considered indeterminate. Any of these forms over here, those are considered indeterminate forms. Also remember that if you get an answer like 0 or 2 or infinity itself, you can stop. You don't have to pursue it any further. There are also some more advanced applications of L'Hopital's rule that you can look into in the book in section 8.7. In particular, when you receive the 0 to the 0 indeterminate form, as seen down here, you might actually, in order to make it a fraction, in order to make your function a fraction, you might have to take the natural log of both sides, which will assist you in doing that. That's something that's a little more advanced, but you can take a look at that and how they did that in the book and how that might apply to some of your homework questions. So definitely take a look at the homework. This is the last topic for Calculus 1. Congratulations for getting through the course. And now on to final exam review.